Welcome to the next video and to a new chapter, everybody. We're going to go into chapter 11 of my notes, which seeks to prove R equals T in the non-minimal case. Today's just going to be an introduction on what our goal is going to be this chapter and some terminology. So let's get into it. So let's remind ourselves what's happening here. Let E over Q be an elliptic curve. The modularity theorem states that E is modular, which means there exists a weight to normalized new form F such that A sub P of F, the P Fourier coefficient of F, is equal to A sub P of E, which is this gadget that's sort of counting mod P solutions to E for all primes P at which E has good reduction. Okay, so in other words, kind of the L functions of the elliptic curve and the new form match up. So let's let L be a prime. Let's choose a basis for the allotic Tate module T sub L of E. And we'll consider the attached allotic Galois representation, rho EL from GQ to aught TL of E, which is isomorphic to GL2 of the allotic integers. I would see chapter 1 of my playlist on Fermat's theorem for information about what the heck I'm talking about here. This is all gone over in pretty careful detail there. Okay. By the fivefold theorem, which is also from that chapter, E is modular if and only if this representation is modular, which essentially means it's equivalent over Q sub L, the allotic numbers, the representation rho sub FL of the canonical allotic representation attached to the new form F for some weight to new form F. Okay, so you can have E modular, which means this, or you can have the representation, the allotic representation rho EL modular, which means it's sort of isomorphic as representations to the natural allotic representation attached to some weight to new form F. Okay, so what will we do? We're actually going to do better than the semistable version of the modularity theorem, and we're going to actually characterize allotic representations that arise from modular forms, not just simply note that these allotic representations attached to elliptic curves over the rationals are among these representations. Since coefficients of a new form lie in a ring of integers of some number field, which may not be Q, this is also discussed in chapter 1 of my playlist, we should actually be considering more general representations that look like, let's say, rho from GQ to GL2 of A, where A is the ring of integers of a finite extension of QL. And then we should ask which of those come from modular forms. Okay. In fact, we'll even go a step further and we'll consider A to just be a complete Noetherian local ring with finite residue field, which we'll call K of characteristic L. Okay. Enter R equals T. Roughly speaking, what we'll need to prove, and which is sort of the main theorem of Wiles here, is we need to show that if we have such a representation rho, which is, let's say, plausibly modular in the language of Ribbit, then if rho bar is modular, so the reduction of rho mod the residue field K, then rho is modular. Okay, so let us return to our elliptic curve E. Suppose we know that rho bar EL from GQ to GL2 of F sub L, so this is the field of L elements, is modular. For example, by Langland's tunnel, if L was 3 and rho bar EL is irreducible. That might be a setup we might find ourselves in. I wonder if that'll come up. A result of this type, okay, would imply that rho EL, hence E, is modular. And so the reality of the situation is we just have to prove this. You have the reduction of your representation is modular, and you have that the representation itself is plausibly modular. You want to prove that the representation must not only be plausibly modular, it must be actually modular. Okay, so what the heck does plausibly modular mean? Well, let's consider representations rho from GQ to GL2 of A, where A is as above, which do happen to arise from weight to new forms on gamma 0 n, where n is allowed to vary, let's say. We're going to build a list of conditions on these representations, which encapsulates their modularity. For example, from chapter 1, we know that we're going to need such rho to be irreducible with cyclotomic determinant. And these representations are going to have to be unramified outside primes, not dividing NL. These are very basic properties of allotic representations attached to weight to new forms. And so those are definitely conditions that we're going to want listed among those that encompass plausible modularity. Okay. Are those conditions enough? It's tempting to call a rho satisfying that kind of brief set of 3 conditions plausibly modular, but it turns out you need one more. Namely, let's suppose that L is odd. We're going to ask that rho be semistable at L. This is a condition we talked about in chapter 1 already, but if you recall, that means it's either flat or ordinary at L. So flat means it's allotic, its QL points come from the QL points of a finite flat ZL group scheme. And ordinary at L sort of means the image of inertia at L is kind of strictly upper triangular. So it's like unipotent. Okay. So we're going to need to add that condition onto the three above. So we want irreducible cyclotomic determinant, unramified outside, primes not dividing NL, and semi-stable at L. Okay, so let's fix an irreducible mod L representation, rho bar from GQ to GL2 of K, whose determinant is the mod L cyclotomic character. Let's let R be the set of isomorphism classes of these plausibly modular rho, which have reduction rho bar. So they reduce down to this given rho bar here. And then let's let T denote the set of genuinely actually modular isomorphism classes in R. Our goal is to prove that R equals T. In other words, everything that's plausibly modular actually is modular. Okay. Let's assume T is non-empty by assuming that rho bar is modular and semi-stable locally at L. Okay, that gives you a non-empty T just by definition. Okay, in fact, it was already known prior to whiles that T is in fact infinite. Ribbit proves this in congruence relations between modular forms, which I'll call RCR from here on out if I need to refer to it again. The problem is, this makes R huge and hard to work with. So what we do is we get a little bit clever here. We place some additional filters on R as follows. Give me a finite set of prime sigma and let R sub sigma be the set of those rho in R which are of so-called type sigma, which essentially means, and we'll specify what this means later, although we touched on this briefly in chapter 1, this really just means they're sort of well-behaved outside this finite set of prime sigma. And then just define T sub sigma to be T intersect R sub sigma. Again, we'll make all these definitions precise later in this chapter, but for now, we'll just remark that, in fact, this is not hard to see, that R is just the union over all possible R sub sigmas. And so to prove that R equals T, what we're going to do instead is prove that R sigma equals T sigma for all sigma. And this turns out to be much easier because these guys are much smaller. Okay. So what is this whole type sigma business? I'll just conclude by briefly introducing this concept, although this is not the concept we'll end up working with ultimately, but we'll say that rho is type sigma if sigma contains the set of prime divisors of the conductor of rho divided by the conductor of rho bar, okay, a conductor of the representations. That's also a concept defined in chapter 1 of this playlist. This quotient, as we saw also in chapter 1, is an integer. So we know n of rho bar always divides n of rho, although this is not super easy to show. But when n of rho is assumed square free, which is what we're going to be assuming because we're going to be working with semi-stable elliptic curves, this definition actually works perfectly. But we will actually, for reasons that will become clear later, have to extend this definition. So this definition, like pseudo, works for now. It's kind of like easy to latch onto, but we're going to have to extend it later. Basically, because we're looking at representations from GQ to GL2 of A for such a broad class of rings A. That's why this definition isn't going to completely work for every argument we make. So what's our goal of this chapter? Again, we're going to deduce R equals T, or rather R sub sigma equals T sub sigma for all sigma in the so-called minimal case, from the so-called minimal case, excuse me, when sigma is the empty set. So we're going to assume R equals T when sigma is empty. We're going to just take that for granted. And then we're going to prove that R sigma equals T sigma for all non-empty sigma, assuming that. And then in a later chapter, we'll deal with the so-called minimal case, which is we'll prove R equals T when sigma is the empty set. But for now, we're going to assume that. Okay, it's a totally kind of different argument when sigma is empty. Okay, so we're going to work on the non-minimal case of R equals T this chapter. We'll start doing that next video. Thanks for watching, and I'll see you then.